Okay. In the previous class, we have learned about the covariance and the correlation, right? And also, we have solved this exam 5-26 about the covariance in the previous class. And today, we are going to calculate the correlation for the same example. For the discrete random variables x and y with the joint distribution as shown in the following figure 5-14, okay? In the case, determine the covariance and the correlation. And we have already calculated the covariation, so we are going to calculate only the correlation in this class. And based on the equation, the law xy is equal to the sigma xy, this is the covariance, over root v x by v y, right? And in the previous class, we have already calculated this value that is equal to 1.26, right? So we will only calculate the marginal variance of x and the marginal variance of y. So firstly, we are going to calculate the marginal variance of x, okay? And in the previous class, we already learned about the marginal variance, the conditional variance, right? Vy given x, okay? And that is equal to the summation of y minus mu y given x squared by the conditional probability mass function of y given x. Okay? So we have already learned about this equation. And in here, this is the conditional mean, right? And for the case of the marginal variation, we can apply the same equation, which means that the Vx is equal to the sigma, okay, x minus mu x, this is the marginal mean, okay, square by the marginal probability mass function. This is the same formulation, okay? And this is over x. In this case, what is this? The marginal probability mass function is equal to the sigma over y f x y x comma y, right? This is the joint probability mass function, right? So the marginal probability mass function of y is equal to the summation over y of the joint probability mass function of x and y, right? So this can be rewritten as the double summation. This is over y, this is over x, x minus mu x squared by the joint probability mass function fxy, right? Okay. And based on this discrete joint distribution graph, the x is from 0 to 3, and y is from 0 to 3, right? So this can be rewritten as y is from 0 to 3, and x is from 0 to 3, okay? And in the previous class, we have already calculated this value, right? The marginal mean. There was 1.8, okay? So this equation will be when x is equal to 0, 0 minus 1.8 square, right? Right? And by when x is equal to 0, we have only one joint probability mass function of 0.2 here, right? right? When y is equal to 0. So the joint probability mass function should be equal to 0.2. Okay? Plus, when x is equal to 1, okay, we have two different joint probability mass functions of 0.1 and 0.1 according to the y, right? So when y is equal to 1, the joint probability mass function is equal to 0.1, and y is equal to 2, the joint probability mass function is equal to 0.1. So this term should be 0.1 plus 0.1, right? Right? And plus, when x is equal to 2, 2 minus 1.8 squared by, we also have two different joint probability mass functions here, 0.1 and 0.1 according to the y. Okay? So this is also 0.1 plus and 0.1. Okay? And finally, when x is equal to 3, 3 minus 1.8 squared by, we have only one probability mass function here, that is 0.4. So if you calculate this based on your scientific calculator, the answer is 1.36. Okay? So this is equal to 1.36. Okay? And now we need to calculate the large V and large Y, right? And this is also the summation over y minus mu y squared by y, right? This is the identical formulation, but x is just changed to dy, okay? And this also can be expressed by the double summation, okay? This is x and this is y minus mu y squared by the joint probability mass function xy, right? Okay. So in this case, the x is also from 0 to 3 and y is also from 0 to 3. This is equal to the double summation. X is from 0 to 3, y is from 0 to 3, and y minus mu y squared by the joint probability mass function xy. So when y is equal to 0, here, when y is equal to 0, 0 minus, what is this? Uy is equal to 1.8, okay? We have already calculated this in the previous class. So 0 minus 1.8 squared by, we have only one joint probability mass function when y is equal to 0 here, that is 0.2 by 0.2, okay? Right? Okay? And plus, when y is equal to 1, 1 minus 1.8 squared by, when y is equal to 1, we have two different joint probability mass functions, that is 0.1 and the 0.1, according to the x, okay? When x is equal to 1, the joint probability mass function is equal to 0.1, and when x is equal to 2, the joint probability mass function is also equal to 0.1. So this is also 0.1 plus 0.1. Okay? Plus, when y is equal to 2, 2 minus 1.8 squared by, we also have two different joint probability mass functions here. So this will be 0.1 plus 0.1 plus, when y is equal to 3, we only have one probability here, that is 0.4. So if you calculate this equation based on your scientific calculator, this is also equal to 1.36. Okay? So the low xy is equal to 1.26 over root 1.36 squared. Okay? Right? And that is equal to 1.26 over 1.36. And if you calculate this, the answer is 0.926. Okay? Which means that the two different random variables, x and y, has a relationship, in the positive direction. Okay? So this is the answer for this question. And now we are going to talk about the different independent random variables. Okay? And for the independent random variables, we do not expect any relationship in their joint probability distribution, right? So in that case, if the two different random variables, x and y, are independent, the low xy should be equal to 0, right? And the low is given by this equation, that is sigma xy over root vx and vy. This cannot be equal to 0, right? Because this is the denominator, which means that if low xy is equal to 0, the sigma xy is also equal to 0. Okay? That is the reason why we have this relationship. Sigma xy and also the low xy, both should be equal to 0. So this is the case of the independent. Okay? And this is the example. Example 5-28, for the case of independence, implies 0 covariance. For the two random variables, as shown in the following figure 5-16, as you can see here, and please verify that in this case, the sigma xy is equal to 0. Okay? And this is, we have two different random variables, that is x and y, okay? And they are continuous random variable. And the joint probability density function fxy is equal to 1 over 16 by xy. So the question is that we have to verify the sigma xy is equal to 1, equal to 0, right? Because this is the independent case. So the sigma xy is equal to mu xy minus mu x by mu y. Okay? We have already learned, right? This is equal to large E and large xy, right? We have already learned. Please see your previous slide. So we need to calculate this term, and this term, okay, to verify this. So we are going to first calculate the mu xy, okay? That is equal to the mean of xy. That is equal to the double integration x by y by the joint probability density function x comma y dx and dy, right? Right? Okay, we have already learned about this in previous class, okay? So, this can be written as the double integration x, y by 1 over 16 by x, y, dx and dy, okay? Because this is the joint probability density function given here. And x is from 0 to 2, right? So the range of the first integration is from 0 to 2. And the second integration should be from 0 to 4, okay? 0 to 4. So we need to calculate this equation to solve the mean of xy. In that case, we can say this is the small a, and small a is equal to 1 over 16 can be extracted, right? Y squared, okay, by integration from 0 to 2 x squared dx, right? We can extract 1 over 16 by y squared because this is a function of x. And this is given the following equation that 1 over 16 by y squared by 1 over 3 by x to third power from 0 to 2. Okay? And that is equal to 1 over 16 by y squared by 8 over 3. Okay? Right? The 2 to third power is equal to 8. And when x is equal to 0, this is equal to 0. So we obtain this form. And this 8 can be eliminated by dividing 16 by 8, and 2 is left. So that is equal to y squared over 6. Okay? So the large E, large X, large Y is equal to the integration from 0 to 4 y squared over 6 dy. Okay? And this is equal to 1 over 6 by 1 over 3 by y third power from 0 to 4. Okay? And that is equal to 1 over 6 by 64 over 3. Because this is 4 to third power, that is equal to 64. And we can divide these two values by 2. And 3 can be left here. And 32 can be left here. So the final answer is 32 over 9. Okay? So this is equal to 32 over 9. And then we need to calculate the marginal mean of x. The mu x is equal to the double integration, right? X by the joint probability density function. Right? Okay? This is the same formulation with the previous discrete case, but the only difference is that the double sigma is changed to the double integration. Okay? This is exactly the same formulation. So this can be written as the double integration, okay? And xy 1 over 16 by xy dx dy from 0 to 2, 0 to 4. Okay? And in here, we are going to calculate this term first. We can say this is the small b. Small b is equal to y over 16 by integration from 0 to 2 x squared dx. Okay? This is equal to y over 16 by 1 over 3 to x to third power from 0 to 2. That is equal to y over 16 by 8 over 3. Okay? So in here, a can be eliminated by dividing 16. 2 is left. So that is equal to y over 6. So finally, the mu x is equal to the integration from 0 to 4 y over 6 dy. Okay? And that is equal to 1 over 6 by 1 over 2 by y squared from 0 to 4. Okay? Okay? So that is equal to 1 over 6 by 16 over 2. And 2 can be eliminated by dividing 16. And these two terms can be divided by 2. So 3 left here and 4 left here. The answer is 4 over 3. So now we calculate this term that is equal to 4 over 3. Okay? And finally, we are going to calculate this term, mu y. That is also the double integration y by the joint probability density function, okay, dx and dy. And this is equal to the double integration from 0 to 4, 0 to 2, 1 over 16 x y squared dx dy. Right? And also, we are going to first calculate this term. We can say this is the c. C is equal to the integration from 0 to 2. This is y squared over 16 by the integration from 0 to 2 x dx. Okay? No, this is the x term, okay? So that is equal to y squared over 16 by 1 over 2 by x squared from 0 to 2. And that is equal to y squared over 16 by 4 by 2. And this can be eliminated, and 2 is left here. And this can be eliminated, and 8 is left here. So that is equal to y squared over 8. Okay? So finally, the mu y is equal to from 0 to 4 y squared over 8 dy, and this can be 1 over 8 by 1 over 3 by y to third power from 0 to 4. Okay? And that is equal to 1 over 8 by 64 over 3. Okay? And this can be eliminated by dividing 64 by 8. 8 is left here. So the answer is 8 over 3. Okay? This is the 8 over 3. So finally, this term, the sigma xy, that is 30 over 9 minus 4 over 3 by 8 over 3. Okay? What is this? 32 over 9. Okay? So this is equal to 0. So for this case, these two random variables are independent, okay, based on this definition. And now, we are going to talk about the linear functions of random variables. So, up to this page, we have learned about the multiple random variables, right? But the multiple random variables are all constant value, right? Okay? But in this case, the random variables can form one linear function, right? So this page is going to discuss about that case. A random variable is sometimes defined as a function of one or more random variables, okay? And the function of random variables is formed by linear relationship in this chapter. Given random variables x1, x2, blah, 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 xp, and constant c1, c2, blah, 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 cp, we can have this new random variable y, and y is equal to the linear relationship of all these random variables. So that is equal to c1 by x1 plus c2 by x2 plus blah, 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 plus cp by xp. Okay? And this is the linear combination of the all random variables. Okay? So in this case, we have multiple random variables of x1, x2, blah, 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 xp, and they have a linear relationship, as you can see here. So we can provide the new random variable y that is equal to this linear relationship. Okay? And for the case of the mean, and for the case of the linear function of random variables, we can also have the mean and variance. If x1, x2, and xp are the random variables, and y is equal to c1 by x1 plus c2 by x2 plus blah, 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 plus cp by xp, the mean of y is equal to c1 by ex1 plus c2 by ex2 by plus cp by exp. Okay? And this can be verified based on the following equation. For example, for the case of the continuous random variable, okay, the large E, large Y will be the integration, right, Y multiplied by the joint probability density function. right? Right? Because the y is a function of these terms, okay? So the mean of y is equal to the integration y by the joint probability density function, okay? And this can be written as the integration. What is the y? Y is C1 x1, right? Plus C2 x2 CP xp by f x1 right? This can be rewritten this equation, okay? And this equation can be also rewritten as C1, the integration x1 by the joint probability density function plus C2 right? Because this is the summation, okay? So we can have Cx1 by the joint probability density function here, okay? We can consider this is one term, and C1 is the constant, okay? So this can be C1 by the integration x1 by the joint probability density function, okay? Plus C2 by the integration x2 joint probability density function, okay? We can apply this case up to the CP, okay? And what is this? That is equal to the mean of x1, okay? And what is this? That is the mean of x2, okay? So this is equal to the mean of xp. So this means that the EY is equal to C1 by EX1 plus C2 by EX2 blah 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 plus CP by EXP. Okay? So for a case of the mean of y, when y is equal to the linear relationship of x1, x2, and xp, the mean of EY is equal to C1 by EX1 plus C2 by EX2 plus blah 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 plus CP by EXP. Okay? So this can be calculated by this equation. And also, what about the case of the discrete random variable? For the case of the discrete random variable, this can be written as the E summation of I is from 1 to P, okay? C I X I. right? Okay? Because y is equal to c1 x1 plus c2 x2 plus blah 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 cp xp. That is the summation of I when I is from 1 to p, ci by xi. Okay? So this is the same equation. And this can be written as the E of C1 x1 plus C2 x2 plus CP xp. Okay? And for the case of the summation, this can be written as E of C1 x1 plus, okay, E of C2 x2 blah 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 E CP xp for the same concept with the previous continuous case. Okay? And in this case, C1, C2, and CP are all constant. Okay? Which means that this can be written as C1 by EX1 plus C2 by EX2 CP by EXP. Okay? So, for the case of both continuous and discrete random variables, the EY is equal to C1 by EX1 plus C2 by EX2 plus CP by EXP. Okay? So we can calculate the mean of Y based on this summation. And secondly, we are going to consider about the variance. Okay? The variance of Y is equal to C1 squared by Vx1 plus C2 squared by Vx2 plus blah 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 plus Cp squared by Vxp plus 2 by the double summation Ci Cj covariance xi comma and xj. And I'm going to verify this equation as well. And to derive this equation, we have to first use the definition of the variation of Y. The definition of variance of Y, okay, sigma y squared, okay, that is the definition. Sigma y squared is equal to large V, large Y, okay, that is equal to the mean of Y minus mu Y squared, okay, this is the definition. So, for this case, we are going to use this equation, that is E, what is the Y? Y is summation of Y from 1 to P, okay, Ci xi, right? That is the Y. Okay? Because Y is equal to C1 x1 plus C2 xp, blah, 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 right? So that is the summation of I, when I is from I to P, Ci xi. Okay? That is the Y. Minus, what about the mu Y? That is also the summation of I, when I is from 1 to P, Ci by mu xi. Okay? Why? Because the mean of Y here, okay, that is equal to C1 by EX1 plus C2 by EX2 blah 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 CP by EXP. That means that is the summation of I when I is from 1 to P CI by the mean of XY. Okay, that is the mu XI. So that is the square. Okay, right? So for this case, this can be written as E summation of I when I is from 1 to P and C I X I minus C I mu X I square. Right? Because this is the same formulation, summation. Okay? So this can be written as this equation. Okay? Okay? And that is equal to the E the summation of I when I is from 1 to P CI by XI minus mu XI square. This is the same constant, okay? So we can extract the CI here, right? So we can written this equation to this. And in here, we can assume that this squared term is divided into two terms, and this is connected as the product, okay? Because this is the multiplication of the summation of I when I is from 1 to P, CI, XI minus mu XI by summation of when I is equal to 1 from 1 to P, CI, and XI minus mu XI, okay? This is the multiplication term. But in this case, since we assume that this equation has the same function as I, we can express this as the square term, right? Actually, this is the multiplication term. So this can be written as the E of the summation of I when I is from 1 to P C I X I minus mu X I by, okay? And summation, we can use the different term, J. J is from 1 to P, okay? C, J, X, J minus mu X, J. Okay? Okay? Because this is the assumption. We assume that the I. But in here, we can divide this equation to this product term. Okay? So, for this case, we can rewrite this equation to the E, the summation of I when I is from 1 to P, and the summation of J when J is from 1 to P, C I by C J by X I minus mu X I by X J minus mu X J. Okay? Right? And in here, this is the constant, okay? So, this can be changed to this equation, the double summation of I when I is from 1 to P, and the summation of j is from 1 to p, ci, cj, and mean of xi minus mu xi by xj minus mu xj. Okay? Okay? Because this is the constant, so for this case, we have two options. The first one is that when x is equal to j, when I is equal to j, okay? We have two options that when I is equal to j and I is not equal to j. We have two options for this case. So when I is equal to j, this can be rewritten as C1 square, okay, by E x1 minus mu x1 square, okay, because I is equal to j, plus C2 square by E x2 minus mu x2 square, blah blah blah, plus Cp square by E xp minus mu xp square, right? Okay? When I is equal to j. And from this definition, what is this? EX1, right? Free x1, free x1. So that is equal to free x1, okay? And what about this? That is equal to free x2, and that is equal to free x3, free xp, okay? So when I is equal to j, we have this formulation, okay? Okay? And when I is not equal to j, okay? For this case, we can have C1 by C2 exponential x1 by mu x1 by x2 minus mu x2 plus, this is the case I is equal to 1, j is equal to 1, 2, okay? And C2 by C1 by E x2 minus mu x2 by x1 minus mu x1 when I is equal to 2 and j is equal to 1, okay? And we can repeat the same process, right? What is this? That is the covariance of x1 and x2, right? Okay? And what is this? That is the covariance of x2 and x1, okay? So this can be rewritten as the double summation, okay, of I when I is from 1 to p and j is from 1 to p, ci, cj, covariance xi, xj, right? Okay? And in here, these two terms are the same equation, right? Okay? So, if we provide the additional condition that the I is always larger than J, okay? We can provide this regulation, new regulation. This can be rewritten as 2 by the double summation when I is smaller than J, Ci, Cj, covariance Xi, Xj. Right? Right? This is the same equation. And from this equation, we have these two equations. But this is the identical equation. For this case, if we provide this regulation that I is always smaller than J, okay, we can eliminate this term because this is I is larger than J, right? And if we provide 2, we can have these two terms finally, okay? So when I is not equal to J, we can obtain this term, okay? So from this definition, from this derivation, we obtain the variance of y is equal to c1 squared by vx1 plus c2 squared by vx2, blah, 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 plus cp squared by vxp plus 2 double summation when I is smaller than j, cj, ci, cj, covariance xi, xj. Okay? But if the random variables x1, x2, xp are independent, for this case, the covariance should be equal to 0, right? So finally, the Vy is equal to c1 squared by Vx1 plus c2 squared by Vx2 by plus blah 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 cp squared by Vxp. Okay? So in the case of the independent, we can simplify this equation to this one, since the covariance is equal to 0. Okay? So this is the mean and variance of the linear function of the multiple random variables. And from this definition, we are going to solve the example 5-33. A semiconductor product consists of 3 layers, and they are independent here. And the variances of the thickness of first, second, and third layers are 25, 40, and 30 nanometer square respectively. And in this case, what is the variance of the thickness of the final product? That is the question, okay? In the case, let x1, x2, x3, and y be the random variables that denote the thickness of the respective layers, okay? And the y is the final product, okay? Then y is equal to x1 plus x2 plus x3. Okay? This is the relationship between these 3 layers, thickness of the layers, and the new random variable y. So for this case, the final product is equal to y. So we need to calculate the variance of y. Okay? And the variance of y is equal to c1 squared v x1 plus c2 squared v x2 by c3 squared v x3. Okay? For this case. And what about the c1, c2, c3? They are all 1. Right? So that is equal to 1 squared by, what is the variance of x1? the variance of the thickness of first, second, and third layers are 25, 40, and 30 nanometer square. So that is equal to 25. Okay? Plus 1 square by 40 plus 1 square by 30. Okay? Right? So that is equal to 95 nanometer square. Okay? Right? So we can simply calculate this equation. And now we are going to calculate about the mean and variance of an average. And if x bar is equal to summation of all probability, all random variables from x1 to xp over p, this is the number of random variables, right? So this is the average, okay? With the mean of xi is equal to mu when I is from 1 to p. In that case, the mean of average of x is equal to mu. And I'm going to verify this. So we need to calculate the mean of average of x, right? And that can be written as the mean of the summation of all random variables over the total number of random variables, p, right? Okay? This equation can be changed to this equation, okay? And in this case, the E by x1 over p plus x2 over p plus xp over p, this equation also can be changed to this equation, okay? Right? And based on the previous definition, the coefficient can be extracted, okay? And the summation can be divided, okay? So this is equal to 1 over p by exponential x1 plus 1 over p by exponential x2, okay? Plus 1 over p by exponential xp, okay? And the mean of xi is equal to mu here, which means that is equal to mu over p plus mu over p plus mu over p. And the number of all these cases are p. Okay? Right? Because we are considering about the xi from xi to xp. So the number of all these terms are p, which means that mu over p by p. Okay? So p can be eliminated. That is equal to mu. Okay? Okay? So we can have the mean of the average of x is equal to mu. And if x1, x2, blah, 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 xp are also independent with the variance of xi is equal to sigma square when I is equal to 1 to p, the variance of the mean of x is equal to sigma square over p. And I'm going to verify this again. the x bar is equal to 1 over p x1 plus 1 over p x2 plus 1 over p xp. Right? Right? Okay. So the variance of x bar, what is this? This is the C1. This is the C2. This is the CP. So the variance of x bar should be equal to C1 square by 3x1 plus C2 square by 3x2 by CP square 3xp. Okay? Because in this case, the random variables are independent, the covariance is equal to 0. Okay? So we don't have to consider about the later term here. Okay? 2 double square CICJ covariance xi xj should be equal to 0. So this is equal to 1 over p square. The Vxi is equal to sigma square, right? By sigma square plus 1 over p square by sigma square. Okay? Plus 1 over p square by sigma square. Okay? Right? So the number of these terms are also p. So 1 over p square by sigma square by p. Okay? P can be eliminated here. So the final answer is sigma square over p. Okay? So if x1, x2, blah, 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 xp are also independent, the variance of the average of x is equal to sigma square over p. Okay? So we can simply use these two terms for the calculation of the average value. And also, we are going to discuss about the reproductive property of the normal distribution. This is about the normal distribution. If x1, x2, xp are independent, and these have the normal distribution with the mean of xi is equal to mu I, and 3xi is equal to sigma I square when I is from 1 to p, we have this relationship. Okay? This is the linear relationship. And the y is also following the normal distribution, okay, for this case. So if the random variables are following the normal distribution, and this has a linear relationship, and we have a new random variable y, okay, this is a linear relationship of all these random variables, we can assume that this is also following the normal distribution. Okay? So in that case, the mean of y is equal to ci mu I plus c2 mu 2 plus blah 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 cp mu p. This is the same formulation with the previous one, right? The ex1 is just changed to mu 1 based on this definition. And also, the variance of y is also equal to c1 square by sigma 1 square plus c2 square by sigma 2 square, blah, 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 plus cp square by sigma p square, because 3xi is equal to the sigma I square. Okay? So we can use the same formulation. And also, the random variable, the new random variable y is also following the normal distribution. Okay? And this is the example. And let the random variables x and x1 and x2 denote the independent lengths and width of our manufactured part. Assume that x1 is a normal random variable, okay? which means that we can use the normal distribution with Ex1 is equal to 2 centimeter and the sigma 1 is equal to 0.1 centimeter and x2 is also a normal random variable with Ex2 is equal to 5 centimeter and sigma 2 is equal to 0.2 centimeter. Okay? So in this case, what is the probability that the perimeter exceeds 14.5 centimeter? That is the equation. That is the question. So for this question, we can have, this is the productive part. This is the manufactured part, okay? And this is the x1 and this is the x2. Okay? And for this case, what is the perimeter? We can say the perimeter is y. Y is equal to 2x1 plus 2x2. Right? Right? So, the question is that the probability of y should be larger than 14.5. That is the question. Okay? Okay? And in here, this is the normal distribution. Okay? And if we change this normal random variable to the standard normal random variable, we can use the appendix table. So this should be changed to the probability of z, which is the standard normal random variable, larger than 14.5 minus mu y over root sigma square. Right? This is the equation for the standardizing method. Okay? Which means that we need to calculate the mu y and sigma y square. Okay? And what about the mu y? Mu y is equal to C1 by Ex1 plus C2 by Ex2. Okay? Right? So, what is the C1? C1 is equal to 2. What is the Ex1? That is equal to centimeter here. Plus, what is C2? C2 is equal to 2. What is Ex2? Ex2 is equal to 5 here. So this is equal to 14. Okay? And what about the sigma y square? That is equal to C1 square by Vx1 plus C2 square by Vx2. Okay? Right? And that is equal to 2 square by, this is the standard deviation, okay, sigma. So this should be 0.1 square, right? Plus 2 square by 0.2 square. Okay? That is equal to 0.04 plus 0.16. So that is equal to 0.2. Okay? So this equation will be the probability of z when z is larger than 14.5 minus 14 over root 0.2. Okay? And that is equal to the probability of z when z is larger than 1.12. Okay? Root 0.2. Because this is the variance, and when we use the standardizing method, this should be root variance, right? So if you calculate this based on your scientific calculator, we obtain 1.12. And for the case of the normal distribution, this is the standard normal distribution. That is, this is the value z, and this is the probability mass function fx. We have this symmetric curve, right? This is the standard normal distribution. And in this case, this is the 1.12. And we need to calculate this shaded area, right? But from your appendix table, this should be always smaller than the value, right? So this should be equal to, this is the minus 1.12. These two area is equal, right? Because this is the symmetric curve. So this can be written as the probability of z when z is smaller than minus 1.12. Okay? And now you can use your appendix table. And if you use your appendix table, the value is 0.13. Okay? So the answer of this question is 0.13. Okay?